Hey there everybody, and welcome to a video on section 4.3. This video is about two topics, the first derivative test and concavity, but they are both related. To figure out concavity, a term I'll define later, you use the same logic as the first derivative test. So what is the point of this section? So many of the applications of calculus depend on being able to think about what f of x is doing given information about its derivative. And so one of the classic applications of calculus is to do what's called optimization. So thinking about maximizing profit, minimizing cost, maximizing revenue, things like that. Those are classic calculus problems. And the reason is because calculus can help you find maxes or mins and decide whether a critical point is such a thing. So the point of section 4.3 is just to investigate what the derivative of f can tell us about the graph of f, and think about classifying critical points as a max, a min, or neither. The second derivative, f double prime, can tell you about what's called concavity, which I'll show you what that means in a few minutes. So this entire section runs on some observations. These 7 observations give us everything we want to know when we define the first derivative test. So if we were in class, I would have you all fill these in, but we're not in class, so we'll just talk it out here. So a function f of x is increasing, so going up, if and only if you should fill in the blank here with a statement about a derivative. And if we were in class, I'm sure that one of you would say that if the derivative is positive. So f of x is increasing if and only if f prime of x is bigger than 0 on this interval. That's what goes here. You're increasing if and only if f prime is positive. So similarly for decreasing, if you are decreasing, then your derivative is negative. So if and only if f prime of x is less than 0 on the interval I is what you would put here. Okay, so your function doesn't have to go up or down, right? The function could be flat. And so you are sort of flat and unchanging on an interval if and only if what you could put here is f prime of x equals 0. So whether the derivative is positive, negative, or 0 tells you what the function is doing, whether it's going up, down, or neither. Okay, so now if f prime of x changes from positive to negative at a particular point, so suppose I tell you, hey, at x equals 2, to the left of x equals 2, the derivative is positive, and to the right, the derivative is negative. Well, if the derivative is positive, that means the function is climbing, and then if it changes to negative, the derivative is falling. So you got this kind of action. If you watch my mouse, up, down, positive derivative, negative derivative, then the corresponding output will be a local max. That's how you get a maximum. You climb up to it, and then you fall down. The way you get a minimum is to sort of fall down and then climb up. So if f prime of x was negative and now it's positive, then you get a local minimum. Now f prime of x doesn't have to go from positive to negative or vice versa. You can have a function that climbs and then keeps climbing. That's what's happening here. If the function climbs and then keeps climbing, it's neither a max nor a min. And similarly, if the function is falling and then continues to fall, it's neither a min nor max. So basically everything from the section just flows from these observations. So once you have these filled in, hopefully the logic of the section flows naturally. Okay, so the first derivative test is designed to think about whether a given spot on a graph is a max or a min. And here's the methodology. You first find all critical numbers of the function. The reason you do that is because if you are looking for a max or a min, the only possible places such a thing could occur is at a critical number. Okay, either your derivative is 0 or undefined at a max or a min, so you need to look for critical numbers. You then set up a table with a bunch of information in it, so I'll show you how this works in a second. But basically the logic is that if you have an interval between critical numbers, so let's say that x equals 2 and x equals 4 are your critical numbers. Between 2 and 4, there are no other critical numbers. Therefore, there's no peaks or valleys. You can't turn the function around. So between 2 and 4, the function either only goes up or only goes down, and you can just kind of test for that. That's all this is saying. So right now, this is kind of abstract. So let's look at an example that implements these 3 steps. And these 3 steps work basically because of those observations from before. So let's look at an example. So you're given a function, 3x to the 4th, whatever. Tell me where that function is going up, where it's going down, where does it have a peak, Where does it have a valley? If you want to optimize the function, where should you look? So step 1 was to find all the critical numbers because those are the places where the function could possibly have a max or a min. So here's the derivative of the function, and I set it equal to 0. Notice there's 12s everywhere, 12, 12, and then 12 times 2. So if I divide by 12, that 12 goes away, that 12 goes away, that's a 2. And then there are also x's everywhere, so I quickly get this equation here, that x times x squared minus x minus 2 is 0, and then x squared minus x minus 2 factors, like this. And so we learn that the critical numbers are negative 1, 0, and 2. Those are the numbers that make the derivative 0. Therefore, these are the only 3 places where f of x could possibly have a max or a min. We're not guaranteed to have a max or a min here, because like we said here, right, you could have a derivative to the left and right of you that's both positive or both negative, but the only possible places for a max or min are here. So now the rest of the method goes like this. You set up a table like this, where you chop the real number line into intervals that span between these critical numbers. So I have an interval here from between negative 1 and 0. These are all numbers between negative 1 and 0. Between 0 and 2 is this. And then to the right of 2, all numbers to the right of 2, all numbers to the left of negative 1. These 3 numbers chop up the real number line into these 4 pieces. And then you just ask yourself, on each piece, is the function climbing or is it falling? And the thing is, on this interval here, let's think about to the left of negative 1. Either the function is always increasing or always decreasing. So let me say that one more time. On that interval, or on any of these 4 intervals, but think about here, the function is either always going up or always going down. So let's see if we can justify that. Suppose that the function went up and then also went down on that interval. Well, if it went up and then also went down to the left of negative 1, there'd be another critical point measuring that. Because if you go up and then go down, there's a max. And that occurs at a critical number. So since there's no critical numbers to the left of negative 1, we can't both go up and go down over there. We must just do one or the other. And so to test whether we always go up or always go down, just pick some number over here. Any number to the left of negative 1 you feel like. So I picked negative 2. So you pick negative 2. You plug it into the derivative. Here's the factored derivative here, right? The 12 doesn't really affect positive or negative, so it doesn't matter. And then here, notice when you plug the negative 2 in, you get something negative. Negative times negative times negative is negative. Therefore, this function is decreasing at negative 2, but it must also be decreasing on this entire interval. It's going down at negative 2, and we just said it's either always going up or always going down in this interval. So since negative 2 caused the function to go down, we know it's decreasing that entire interval. So basically you set up a table like this, where you use the critical numbers to chop the real number line into discrete sections. And then you just, in each interval, pick a test point and just see, oh, at that point, is the function going up or down? You have to test that by plugging into the derivative, because the derivative tells you about going up or going down. You don't plug negative 2 into like the original function. The original function is not going to tell you if the original function is going up or going down if you plug a number in. If you plug in negative 2 up here, you're just learning that negative 2 something is on the graph. You don't know about going up or down, though. The derivative tells you about going up or down. Okay, it's also worth pointing out on an exam, you don't need to actually multiply this out if you don't feel like. You can just say negative, negative, negative is negative. So similarly here, between negative 1 and 0, pick a test point. So I picked negative half. Okay, so if you plug in negative half into this derivative here, where again I'm ignoring the 12 because that doesn't affect the positive or negative. You plug in negative half there, you get negative half times minus 2. So this is negative. This is negative. That's positive. So negative, negative, positive is positive. We don't actually care what this number is. All we care about is positive or negative. So we know it's positive. So between negative 1 and 0, the function is going up. Okay, between 0 and 2, let's pick a test point. So I picked 1. 1 is a nice number. If you plug in 1 into this Derivative here without the 12, you get negative times positive, which is negative. And finally, between 2 and infinity, pick any number you want. I picked 3. If you plug 3 in here, you get something positive. So what we've learned is that this function, this f right here, the way it behaves is it goes down for a while, and then right at -1, it starts going up. Derivative is positive. And then at 0, it starts going down again. And then at 2, it goes up again. That's what's happening. And so this information allows us to say when the function has a max, when the function has a min. So I'm going down, then going up. That's what it means to have a local min. And then at 0, see, -1, 0, and then 0, 2. At 0, I was going up, now I'm going down. That's how you get a local maximum. And then at 2, I was going down, now I'm going up. That's how I get a local min at 2. This is the first derivative test. It's a way of figuring out where a function has a peak, where a function has a valley. So just to quickly summarize the method, it's always these steps. You find the critical numbers by setting the derivative equal to 0, in this case. And once you have those critical numbers, you chop the real number line into disjoint intervals here, intervals with no overlap based on these numbers, everything between these numbers. And then you pick numbers in each of these intervals that act as kind of test cases or test points, plug them into the derivative and see if you get something positive or negative. And based on that, you know if you're increasing or decreasing on this entire interval. Okay, there are lots of things that can go wrong here, as you might imagine. You just have to practice doing this a few times and the method becomes pretty natural. So for example, you don't want to plug in -2 into the original function, as I already said, because that won't tell you about going up or down. You don't want to plug 0 into the derivative. Some students do that. If you plug 0 into the derivative, you're just going to get 0 back, right? If you plug 0 in here, you get 0 back. And all you've learned is that the derivative is 0 at 0. But we already knew that. We're trying to think about where the function is going up or down. So to think about that, you have to look away from the critical numbers to instead numbers in between, test numbers in between the critical numbers. So like 3, that's not a critical number. It's a test case for this entire interval. 1, that's not a critical number. It's just a test case for looking between 0 and 2. Last thing I'll say about this example, on your own papers, you of course don't have to like label these steps if you don't want to, but I do want to see this derivative equal to 0 step. I want to see this table. I want to see work like this so that I know you're plugging values into the appropriate function. You're not plugging values into f, but instead into f prime. I want to see that. So basically what's on the screen here is what you would need to write. Show you another example. Oh, sorry, one last comment. Some students see, oh, this is negative. That was the first thing I learned. So like, I know it's decreasing from negative infinity to -1, and then you see this alternating pattern. So going down, going up, going down, going up. So if we were in class, I can almost guarantee you that somebody would ask me, well, doesn't that just always happen? And then like, did I even need to bother figuring out the next 3? Don't these things just alternate? And the answer is no. So depending on what the original function is, you might get like all pluses here or all minuses or 2 pluses in a row, 2 minuses in a row, who knows? So let me show you an example like that. Same idea. So I've given you now not the function itself, but I told you its derivative. On an exam, by the way, this is probably how you'll be handed information because it makes the problem go faster. Like back here, we had to find the derivative and factor, and we had to make sure we factored properly. So of course, if you make a mistake here, then it'll throw the whole problem off. So notice this one, I'm just giving you a factored derivative straight up. So I'm saving you some work. So now step 1 is just set that factored thing equal to 0, and you can just read off the critical numbers now. And then the rest of the work is similar. So to the left of -1, between -1 and 3, between 3 and 5, to the right of 5, you pick a test value in each interval, plug it into the derivative, and just see what you get. So over here, you can pick any number you want. To the left of -1, I picked -2. If you plug in -2, notice this is something squared that's never negative. So like, I know this is positive no matter what. And now this is negative. This is also negative. So positive times negative is positive. So I'm increasing to the left of -1. Now between -1 and 3, I could pick any number I feel like 0, a half, 1, 2. I picked 0. You plug 0 into the derivative up here. You plug 0 in, so something squared is not negative, so that's positive. This is negative. This is also negative. So positive, negative, negative is still positive. And so the function is still increasing when you cross that x equals -1 barrier. So the function was going up to the left of -1. It's still going up to the left of -1. And now you can ask what happens between 3 and 5. Once you hit x equals 3, what happens? So between 3 and 5, pick your favorite number. It's probably 4. So I have positive times negative is negative. So the function is going down between 3 and 5. And then to the right of 5, pick your favorite number, plug in 6. You get positive, combines to be positive. Okay, so notice there is no max or min at -1 because the function just went up and it kept going up. So it didn't go up and then go down or vice versa. So -1 has nothing going on. It's not a max or a min. There's a local max of 0 and a local min of 5. So at 5, it was going down, then going up. That's how you create a valley. Okay, so that's the first derivative test. So generally speaking, the homework is like this. Hey, here's a function. What are its maxes and mins? Where's it increasing or decreasing? You got to do this methodology. So let's finish up by talking about the concept of concavity. So the basic idea of concavity is that if a function is increasing, that increase could either be accelerating or decelerating. And same thing with decreasing. So concavity is kind of like a measure of acceleration. So it is a second derivative kind of thing. And so as you might expect, second derivative tells you about acceleration on some level. And basically what's happening is if f prime of x is increasing on I, then you're concave up. So f prime increasing means like you're speeding up. It's like accelerating. And you're concave down if your second derivative is negative. So f prime is decreasing. If f prime is decreasing, it's like you're slowing down. So geometrically, a function is concave up, respectively down, if the graph lives above its tangent lines or below. I'll show you a picture of that in a second. And if you get a change of concavity, it's not a max or a min anymore. It's what's called an inflection point. If you are asked to think about intervals in which f of x is concave up or down, we do the exact same thing we did here, but this is now the second derivative. This is now the second derivative. You just do the same methodology, but think about second derivatives now, because f double prime will tell you where f prime is going up or going down. Okay, so just to show you pictorially what concavity looks like. So I think of it in terms of frowning or smiling. So this graph is frowning here, but then right here, it switches to smiling. So frown is concave down, then there's an inflection point where it switches from frowning to smiling. And notice, when a graph smiles at you, the graph lives above its tangent lines. When a graph frowns at you, it lives below its tangent lines. So that's the idea of concave up or down. Here's another such picture. So here, on this red, if you were to draw tangent lines, the graph would live above the tangent lines, but right around here, it switches to where the tangent lines are above the curve, and it's like frowning at you. And then right around here, it switches to smiling again. Right around here, switches to frowning. So this graph is like smile, frown, smile, frown. And there are 3 inflection points. Whenever you get a color change, that's an inflection point. And just to emphasize acceleration, so these two graphs, sorry for the image quality, but the black here is the actual graph. See that? See that? So notice these left two graphs, they are both increasing, like the black is going up, but they're increasing in different ways. So this bottom graph, it's like accelerating. The growth is getting faster. And you can see that f prime is increasing. These tangent line slopes are getting bigger. Whereas here with the blue, the tangent line slopes are getting smaller. So it's like you're decelerating. Even though you're still increasing, you're decelerating, versus here you're increasing and accelerating. And same thing over here. Okay, so let me wrap up with an example of finding intervals on which you're concave up or concave down. not increasing or decreasing this time. And let's think about where the inflection points are. So I haven't told you what f of x is because I don't actually care what it is. What you need to know is derivative information. So this, again, is most likely how you'll be handed information on an exam for a problem like this. So let's say that's the derivative, and therefore this is the second derivative. So if you want to, you can verify that if you differentiate the f prime, you get this f double prime. Okay, so now we just do the same process we did before, but with f double prime. So we take f double prime, set it equal to 0, see what we get. We get 3 and 5. We set up this table where we chop the real number line into intervals based on these two numbers. So to the left of 3, between 3 and 5, to the right of 5. And now we plug test numbers into f double prime instead of f prime. So between negative infinity and 3, a good test number is 0. If you plug 0 into the second derivative, you get negative, negative, which is positive. Between 3 and 5, a good test number is 4. So you get negative times positive is negative. Between 5 and infinity, 6 is a good number. Positive, positive is positive. Okay, so the thing is concave up on 2 intervals and then concave down between 3 and 5. So if you were to ask a calculator to graph f, whatever f is, you would see that it's like smiling at you most of the time. Between negative infinity and 3 is smiling. Then it's unhappy for a short time between 3 and 5. And then it switches back to being happy. So anytime it switches, happy to sad or vice versa, you have an inflection point. So there's an inflection point at x equals 3 and also at x equals 5 because of the switches here. So like if these were all 3 pluses, instead of like an alternating, if it was all 3 pluses, there would just be no inflection points because there'd be no switch. You have an inflection point if concavity switches. If this right here, this were a plus and this were a minus down here, so it's like plus, plus, minus, there would be no inflection point at 3 because there was no switch. But there would be an inflection point at 5. Okay, that is section 4.3. So the main takeaway for you is I should be able to give you a function like that and say, where is it increasing, decreasing? Where is it concave up, concave down? Does it have any maxes? Does it have any mins? Does it have any inflection points? And you should be able to follow this methodology to do that. So here I just gave you the function and you had to find the derivative. And if I asked about concavity, you'd have to find the second derivative. So you'd have to do like 36x squared, that kind of thing. So otherwise, though, I could give you derivatives or give you second derivatives and have you do the same thing. But basically, this methodology is the point of the section, whether you're doing the first derivative to do increasing or decreasing, or whether you're doing the second derivative to think about concavity. As always, if there are questions or anything, make sure you shoot me an email. I could potentially meet with you on Zoom while I'm gone, depending on the time. If you don't want to shoot me an email, you could always ask questions when I get back. But that is the end of section 4.3.